Okay, so we continue. For the substrate for SSF, they must have a common feature, which is basic macromolecular structure. Substrates for SSF are composite and heterogeneous products, means that they are the combination of several elements, not just one element. So you can get the substrate from agriculture or byproducts of agro industry. For example, sugarcane bagasse. The sugarcane, when you press, you get the water and you throw the rest, right? That one is sugarcane bagasse. You can also have inert fibers, means that you need to add your own nutrient and also resins. The basic macromolecular structure, for example, cellulose, starch, pectin, fibers, and so on, confers the properties of a solid to the substrate. Means that if your fermentation requires this kind of solid or substrate, you can tailor specific substrate for them, because different bacteria, different fermentation will require different substrates. Okay, the structural macromolecule may simply provide an inert matrix. Okay, so example this one, inert, within which the carbon and energy source are absorbed. So you need to supply your own carbon and energy source. But generally, the macromolecular matrix represents the substrate and provides also the carbon and energy sources. But it means that usually the solid substrate that you use, they are not inert, they already have the nutrients that is required by the microorganism. Sorry. Okay. So next one. This is an example. For example, the sugarcane bagasse is tea waste, wheat bran, sawdust, apple pomace, and coral cake. Okay, smaller particles are favored due to increase in surface size, can be too small. Preparation and pretreatment represent the necessary steps to convert the raw material substrate into a form suitable to be used for the fermentation. For example, stress reduction, physical, chemical, or enzymatic hydrolysis to increase the substrate availability by the fungus, supplementation with nutrients, pH, and moisture content through a method of mineral solution, cooking or vapor treatment for macromolecular structure pre-degradation, okay, and elimination of major contaminants in the solid substrates. Okay, so this is the examples of the microorganism used during the SSF. Okay. Filamentous fungi are the best adapted for solid state fermentation, not bacteria, because like I said before, the water activity is low in SSF, and also SSF actually they mimic the natural environment of the fungus, not bacteria. Koji and tempeh are the best example. Aspergillus oryzae is grown on wheat bran and soybean for koji production. Okay, for example, for soy sauce production. Tempeh is grown on the soybean as well as the food using Rhizopus oligosporus. Okay, so this is the example. You can read it by yourself. Okay, another example. Okay, example of the strain of fungi and also the processes that they conducted. Okay, you can read it. You can read this one by yourself as well. Okay, so you can read the advantages and disadvantages. They are quite straightforward. Okay, again, some examples. Okay, examples again. Okay, now we are going to learn about the different bioreactor system. Basically, different researchers, they have different ideas of what are the kind of the bioreactor system. So I just take 6 of the major ones. Okay, sorry, this is actually not complete yet. Okay, you can find this description in the next slide. So I will delete this one first. Okay, so basically there are 6 different types of bioreactors. The first one is continuous tank bioreactors, the one that we see in the biotechnology faculty that we visit. Second one is bubble column bioreactors, where they use the bubble to mix the content. Third one is air lift bioreactors, where they use the air to actually mix the content. The next one is fluidized bed bioreactors, where they use is actually quite similar to airlift, but the design is a bit different. The next one is packed bed bioreactors. They use packed beads to actually and pass through the nutrients through the packed bed beads to induce a reaction. And the last one is photobioreactors. They are using lights to induce the reaction of enzyme in microorganism. Okay. So this is the first one, the stirred tank bioreactors. The design is like this. You will have the motor to actually move the stirrer. You also have the jacket to control the temperature, and you also have different pots to put in to insert the nutrients or to take out the sample, or also to put in some air for the as the to insert the oxygen inside the fermentation tank. Okay, so they will have vessel, cylindrical vessel with motor driven central shaft. They also have different type of impellers. This one different shape, because different shape will induce different kind of reaction from the microorganism. They will also have efficient gas transfer to growing cells, good mixing of the contents, and flexible operating condition. This is the most common bioreactors used in the industry today. Okay, so you can read the main features. Okay, like I mentioned to you before. Okay, the second one is bubble column reactor. The design is quite simple. You just use the sparger to produce the bubble that will actually mix the content. Okay. The air or gas is introduced at the base of the column through perforated pipes or plates from metal microporous sparges. The flow rate of the air or gas influences the performance factors, for example, the oxygen transfer and mixing. The bubble column bioreactors may be fitted with perforated plates here. Perforated plates means that the plates that have the holes that will produce more bubbles, okay, to improve the performance of the bioreactor. Okay, the next one is airlift reactor. Okay, so these are the examples of the airlift reactor. The medium of the vessel is divided into two interconnected zones by means of baffle or draft tube. Okay, so for example, this is the baffle or the draft tube. Okay, means that they separate the place where you put in the gas and also where the medium will flow. Okay, so this is the buffer or draft tube. In one of the two zones referred to a riser. Okay, refer to the riser. As you can, it can rise when you supply the air. Okay, the air or gas is pumped. The other zones that receive no gas is a downcomer, where your medium or your nutrient will come down after it being circulated by the gas. The dispersion flows up the riser zone while the downflow occurs in the downcomer. Okay, so quite straightforward. Okay, fluidized bed reactor, they are actually comparable to bubble column bioreactor, except the top position is expanded to reduce the velocity of the fluid. Okay, so you still pump some of the gas, I guess, but the design here is different. Okay, to reduce the velocity of the fluid, so they are slower. Design so the solids are retained in the reactor while the liquid will flow out. Suitable to carry out reactions involving fluid suspended by catalyst. Okay, they are suspended in the water, but then this one is solid. Okay, this one is solid, but the others are solid. They are suspended, such as immobilized enzymes, immobilized cells, and microbial flocks. Gas is usually supplied to create a suitable gas, liquid, solid, fluid bed. Okay, sometimes we supply gas as well. So they have all three components: solid, fluid, and also gas. Okay. It is also necessary to ensure the suspended solid particles are not too light or too dense. Too light, if it is too light, it may float, whereas the dense ones may settle at the bottom. Okay, if it is too light, it will float and cause it to be out, while if it is too heavy, it might be suspended here and no good mixing can be achieved. Okay, next one. Okay, pack of fixed bed reactor. Okay, it is a bed of solid particle here. They are immobilized, not the same as fluidous bed. Fluidous bed, they means they are suspended inside, they can move around. But this one, they are immobilized, they are stick at one place with biocatalyst or within the matrix of solid packed in the column. Okay, inside here you immobilize a biocatalyst. So what happens is you put in the nutrients through the packed bits with biocatalyst, and the one that comes out actually you supply the substrate through here, the one that comes out is your product. Okay, sorry, neutron broth is actually supplied on top, okay, and it will go through here, and the one that comes out is your product. The solid used may be porous or non-porous gels, and they may be compressible or rigid, okay, depending on your experiment. The nutrient broth flows continuously over the immobilized catalyst, and you will get your product because the biocatalyst will convert your nutrient broth into the product you want. The product obtained in the packed bit bioreactors are released into the fluids and can be removed. Okay, the last one, the photobioreactor, is actually very similar to the first one, which is a stir bioreactor. The exception is the outside, they must be made from glass or plastic that can be see-through. So when the light is being shined through this bioreactor, it can go into the reaction. Okay, so usually this kind of bioreactor is being used for the microorganism that requires the light. Okay, for example, algae and so on. So it is carried out either by exposing to sunlight or artificial illumination. But since the artificial illumination is expensive, the outdoor photobioreactors are preferred. Certain important compounds are produced by employing photobioreactors, for example, carotene and this kind of elements that can only be produced by algae. Okay, they are made up of glass or more commonly transparent plastics. So this is one of the example on how you upscaling the bioreactor system. You will start from the experiment first, laboratory scale, small scale. Strain selection, medium development can be up to 2 liters, okay, depending on how big your conical flasks are. Okay, or you can use a very small bioreactor. Then you can go up one level, which is a bigger one, the one that we saw in the biotechnology faculty. Okay, Halal Institute. Okay, you can go up to 5 to 200 liters, and finally you can bring this to much bigger bioreactor, for example in the factory and so on. You can go up to 100 K, I think 100 liters. Okay, sorry, K, 100 liters. Okay, so that's all for lecture week 9 and 10. For you to actually get more information, you can always find them in YouTube. They have plenty of information that is more up to date and I think easier to understand compared to the way I give you the lecture. Okay, because I actually prefer face-to-face lecture compared to online lecture. Okay, so I will see you in the next lecture, which is week 12. Okay, thank you.